we're going to go to our next story, which I'm very excited about because I don't know what any of it means.
Yeah.
The headline on our second story, scientists just made the first time crystal that you can see. We have an ocarina of time.
Yes.
Physicists at the University of Colorado Boulder have created the first time crystal that humans can actually see using liquid crystals that swirl into a never-ending pattern when illuminated by light. They put out their paper in Nature Materials. There's been a lot of coverage of this one.
Yeah,
I always
this
see all
is a
these
big one.
TikToks
I
about
really love it.
time crystals and all this.
Yeah, it's very Marvel, very
yeah.
Doctor Who.
Yeah.
This is how we beat Thanos.
Mr. Strange, Doctor Strange.
Yeah, all
stuff.
sorts of,
So help me understand, what exactly is going on with this time crystals paper?
Yeah, so, well, first, let's talk about what are time crystals.
I would like to know that.
Okay, so before we even do that, normal crystals, okay? We talked about diamond the other day.
Yes.
The simplest crystal I can think of is table salt,
Okay.
NaCl, sodium chloride. You can imagine there's a sodium atom and a chlorine atom. Sodium atom, chlorine atom. Sodium atom, chlorine atom. In this regular sort of chessboard-like structure, but a 3D sort of chessboard of sodium, chlorine. The reason why this is a crystal, right? What characterizes it as a crystal is you've got a discrete space symmetry breaking. Okay? This is a technical term in physics that just means if I take the crystal and I move it over by one spacing, I will get the same thing back. Okay? You can imagine I've got the NaCl and then there's another NaCl here, right? I can take that entire crystal and move it by a whole molecule and I'll have the same thing repeating, right? Just like in a chessboard, right? Imagine an infinite chessboard. That thing is a crystal in some sense, right? It's a 2D crystal because there's black, white. If I take up the chessboard and I move it over two sort of squares, I'll get the same exact chessboard.
Understood.
Right?
Yes.
So that's what's called symmetry breaking in space. Okay, where it's no longer continuous because you can't just arbitrarily move this thing around. You have to move it by the lattice spacing, right? The lattice constant of the crystal.
Yes.
So that's what makes it a crystal.
Okay.
And it's also resilient to forces and stress, right? Like a diamond, for example, great way. I put stress on it. The crystalline structure of the carbon atoms isn't really going to change because the way that these carbon atoms are bonded to each other, they're resilient to like push and pull. Heat it up, that structure is going to be resilient.
Yes.
Right? So there was a guy, Frank Wilczek. He was a Nobel laureate. He won the Nobel Prize in 2004 for discovering something called asymptotic freedom, which has to do with the ways that quarks behave inside the atomic nucleus. We can get into that some other day.
I think we need some asymptotic freedom in the U.S. right now, but that's a whole nother story.
That's a whole nother story as well for another day. But he won the Nobel Prize in 2004, and he's been very active in physics ever since. He's discovered things called axions, and he's done stuff with cosmology. And one of the things that he proposed back in 2012 was this idea of a time crystal. Okay, so he figured it's a very interesting, quite simple argument. Okay, he said that the laws of physics are symmetric to space translations, right? Meaning, if I do an experiment here, and then I take up the experiment and I move it somewhere else, the results of the experiment should be the same, right? If all the environments are the same, and that's because there's no special coordinate in the universe, right? There's no it's just here is where things happen, right? There's no special spatial coordinate. Well, similarly, the laws of the universe are also symmetric in time, right? If I do an experiment now and then I do it the next day, it should be the same.
Yeah.
So if we have things that break spatial symmetry by creating crystals in space, right, where you have clearly carbon,
Yes.
making the diamond, or NaCl making table salt. So you clearly have spatial crystals. What if I have a breaking of the time symmetry to create a time crystal? And what would that look like? What that would look like is you've got some kind of periodic system that returns to its original form periodically, right? So just like how with a space crystal, like the chessboard, I can take it up and I can move it in space and then put it back and it'll be the same thing. In time, for example, a sine wave, right?
Yeah.
Mathematically, a sine wave is symmetric in time
Yes.
to that period,
Yes,
right? I can
exactly.
pick up the sine wave, I can move it one entire period and put it back, and it'll be the same sine wave.
Yes.
I should be able to have that in like the physical world. Okay.
Interesting.
Because, it's kind of same,
Yeah.
right?
Theoretically,
It
makes-
should be possible. And it kind of makes sense. If I have the same sort of symmetry breaking in space, I should have the same sort of symmetry breaking in time. Well, it wasn't quite that simple. Okay?
Never
So right after he published that, it was Frank Wilczek is doing this, Nobel Prize winner. He's a very famous physicist. So everyone's like, okay, is this possible? And actually, it turns out the way that he had envisioned it, it is not.
Okay.
So people came out and they published something called the no-go theorem for time crystals, which was that Frank Wilczek's original idea was that this time crystal is going to be in the ground state, which means it's in its lowest energy state. There's nothing pumping on it. It's just, crystals can be in their lower energy state, right? I can cool a crystal down to like near 0 Kelvin and it's going to remain in its crystal form. And that's what really, that means that it's an inherent property of the material itself, right? And it's not something that coming from outside creating this order.
Mm-hmm.
Frank Wilczek's idea was that you can have a system that is in its ground state, right? In its lowest energy state, there's nothing coming in, and it's still going to behave in this sort of periodic manner.
Yes.
Okay? That turns out can't be the case.
Okay.
Okay? So the no-go theorem said that a true equilibrium ground state cannot have persistent periodic motion. Meaning, if you've cooled something down to its ground state, it's going to be stationary.
Right.
And that kind of makes sense, right?
Yeah.
Because if it's moving around in its ground state, that means there's some kinetic energy that I can extract, and it's not really the true ground state.
Yeah.
Right? Okay, so that's fine. But then people started wondering, all right, fine. I don't need something to be in equilibrium at its ground state. Mm-hmm. What if I pump it with stuff? Can I create a crystal that way? What if I pump it with energy so it's now a non-equilibrium state? Like there's energy coming in and then there's energy going out. But the way that this energy is transformed inside the system creates this periodic motion within the system, right? Turns out that was possible.
Okay.
And for the longest time, people were studying these things called discrete time crystals. They were systems that were kept out of equilibrium by this outside force. And it's not as simple as just like you just pump it rhythmically and then this thing goes by that.
Yeah.
Then it's like, like me on a swing, like doing my legs is a time crystal, right?
That's
like me at the playground is a time. No, that's not. It's not quite as simple.
Okay.
What you need is you need the pumping to be done at a certain frequency, and then the crystal itself is doing it at a different frequency. Maybe it's at a harmonic, right? Mm-hmm. And there were specialized quantum systems that could do this, right? There were nuclear spins, trapped ions, cold atoms at extremely low temperatures, quantum weirdness. It's like cool.
Yeah.
But it's cool.
Yeah.
But that's about it.
Yeah.
Right. Like maybe in 100 years it can lead to quantum devices and things like that. This paper is very cool because it's doing it in a classical system, which means no quantum weirdness, and it's doing it at room temperature.
Wow.
And it's doing it at a big enough scale that we can see with our naked eye.
This is giving me LK99 vibes.
But this is out of UC Boulder.
Yeah, so it's legit.
And so it's pretty legit. UC Boulder has probably the best AMO department out of anywhere in the world. Okay? Atomic Molecular Optical. Those guys do it.
Let's invest in our university research institutions.
Yeah, Boulder has the most PhDs out of any city.
I heard this recently.
Yeah, and a lot of it has to do with UC Boulder. Out of UC Boulder came NIST, which is the National Institute for Standards and Technology.
Yes.
There's a bunch of other science labs just in Boulder. UC Boulder itself has 4 Nobel Prizes in physics just for AMO. Okay, there's one for cosmology, it's just all in the lab making materials, right? They made the first Bose-Einstein condensate. They're the ones who figured out how to trap ions using lasers and cool them down using lasers. So they're a very good. So when a paper comes out of UC Boulder and it's an AMO, it's these guys probably talked to their department, and if it didn't pass their
own, they have the best in the world there.
Yeah. It's So it's a really cool little thing that they've made out of liquid crystals, right? These are the LCDs, and they made a macroscopic time crystal. Okay, and what you can do is what's really cool is, first of all, you don't need a laser or oscillating magnetic field like in those old time crystals. In the old ones, you needed a quantum system and you needed a laser, which means coherent light of a single frequency, and then or like a magnetic field, it's oscillating at a single frequency, and then that sort of drives this quantum system to do this periodic motion. This is just like a light. You just shine a light on it, and then it uses the energy from that light to create this periodic motion. Okay,
this is really cool.
It just uses LCD, like liquid crystal technology, pneumatic liquid crystals. So the way that liquid crystals work, like you've used liquid crystals before. It's a really simple technology. It actually won the Nobel Prize. The idea is, so what does it mean by a liquid crystal? Okay, a crystal you usually think of as a solid.
Yes.
Right. A solid meaning that you've got atoms in a regularly spaced pattern and they don't really move. In the liquid crystal, you've got molecules that are all sort of, you can think of them as like rods, many tiny rods. They're molecules that are elongated, and you can manipulate their direction using an electric field. Okay? So if you put an electric field in this direction, all of the molecules align in that direction. And you can have an electric field in this direction, which means all the molecules align in this direction. And what these molecules do is, because they're small enough, they can actually influence the propagation of light. Okay? And so that's exactly how liquid crystal displays work. What you do is you have a backlight, okay, that and then you have a polarizer that polarizes all the light, so all of the electric fields are propagating in one direction. And what you can do is you can have a liquid crystal interface in between another polarizer. So now, if the light gets to the other polarizer and it's polarized in the same direction, it's going to be let through. But if the light is polarized in a different direction, in the perpendicular direction, then it's going to be blocked. And what you can do is use an electric field to manipulate the liquid crystals in the middle to influence the propagation of light
on the other
That's
side.
the fundamental technology.
That makes sense.
Okay, so you can have an electric field that sort of rotates the light, and then if it rotates in exactly the right way, then the light is going to go through and I'm going to see something. But if there's no electric field, or if I make the electric field this way, then all the rods are going to be sort of in the perpendicular direction. The light is not going to rotate and I'm going to get blocked.
Yes.
And that's fundamentally how liquid crystals work.
Yes.
They're liquid in the sense that, just how in a liquid the molecules can move around.
Yes.
In this case, these liquid molecules, these rod-like molecules, can move around, and they can be controlled by an electric field. And they can be controlled by light itself, right?
Yes.
So they figured what I can do is I can create a liquid crystal, and this liquid crystal has exactly the right properties where it can sort of act like a giant sort of, I guess, okay. So this liquid crystal can be oriented in such a way that when it's shined on by light, what you're going to get is deformations in the crystal.
Yes.
Okay, tiny little deformations. So what you can imagine is, let's say all of the liquid crystals, all of these rods are oriented in one direction. Okay, and now what I do is I introduce a tiny kink in this lattice. So they're all oriented in one direction, but I've taken like a tiny little neighborhood and I've like bent them in a certain way. Okay, what you can do is create a material such that bend, which becomes this sort of topological defect.
Yes.
This like idea of like, okay, this neighborhood has a tiny little bend or a twist. That twist can then influence the stuff around it, which can influence the stuff around it, which can influence the stuff around it. And what you get is this sort of traveling wave of disturbance.
Yes.
Okay? They're what are called topological solitons in physics. This idea that like I've got this like disturbance, and that disturbance kind of acts like a particle. Okay? Because it travels the same way as a particle. The orientation of that disturbance can have a charge, in the sense that if I twist it clockwise, then it's a plus one.
Right.
And if I twist it counterclockwise, it's a minus one. And that charge is conserved in the same way that sort of charge is conserved if I were to have like electrons moving around, right? And they can cancel each other out, kind of the same way that charges cancel each other out, right? So they created this thing, and they actually did the numerical calculation. So they wrote down an equation for how these solitons would interact with each other, and all of these deformations act like little quasi-particles that interact with each other and have a physics to themselves.
Yes.
That is an emergent property of the little tiny rods themselves.
That initial disturbance that has now created a cascade.
Yeah.
That is now independent of the initial source necessarily being.
Yeah.
an
And
instigator.
it's like it's on top of the rods themselves. The rods actually aren't the particles anymore.
Yeah.
It's like the way in which the rods are oriented becomes a particle mathematically.
Okay, yeah.
Right? You can describe the twist itself as this thing that propagates rather than the rods, because the rods are just staying where they are. Right? That's what the crystal part of it.
Right.
But the way that the rods move, that disturbance moves around like a particle.
This is really,
Which is kind of cool, right?
No, that's very interesting.
Yeah, dude, solitons have been around, I think in the 1800s, there's this British guy, I forget his name. Maybe we'll put it up.
Yes.
But it's a funny story because what he saw was he was these British physicists back in the day were very rich, right?
Yeah.
So he's on horseback in the countryside, right? And he's on horseback, and he sees a canal, and then there's a boat, and the boat breaks suddenly, okay? And when the boat breaks suddenly, it created this wave, and he noticed that the wave just kept propagating. And then he was on horseback, and he's got nothing to do. He's probably, got an estate that gets him money,
Yes.
in Downton Abbey or whatever. So he's like, "Fuck it, I'm gonna follow this wave." And he followed it for 2 miles. There was a wave that kept reinforcing itself, and it acted kind of like a particle, right? In the sense that the wave didn't really dissipate until 2 miles later, and he could follow this thing, and he discovered the first soliton.
Okay.
There's a little plaque where he lived, where it's
yeah.
this is the guy who discovered the first soliton. And ever since then, they've been observed in all sorts of material sciences.
Yes.
We've observed them in biology and quantum systems, and this is exactly one of those things where
Got it.
there's a wave that's being propagated, and that wave sort of reinforces itself because of the way that the medium itself works.
Right.
Right.
It is a combination of that input and the structure of the medium.
Yes, exactly.
The liquid crystal.
Yeah.
And the structure of the liquid crystal enables it to continue the propagation of the wave independent, as an emergent property of the structure's initial condition.
Exactly. Yeah. And so they figured that they could use this to make a classical time crystal.
Right.
Because this is not quantum.
Right.
This is just the rods themselves are many atoms big.
Right.
So these guys are interacting through just classical effects.
Yes.
Right. And so what you can do is you can have a liquid crystal embedded inside glass, right? That have these 2 layers, and as one layer sort of moves, it influences the light on the other layer, and then that thing moves, and there's this feedback cycle, right? And that feedback cycle is what creates this propagation of the time crystal. And it's really a space-time crystal, because what you're seeing,
Right.
you can actually look at the videos, and you can see this the colors move in real time, and the wavelength is about 0.5 millimeter to 1 millimeter, which means you can see it with your naked eye, and it's moving through this liquid crystal in this sort of propagating traveling wave, right? And it was huge, because one of the big things that defines a crystal, right, is it has to be, as I said before, crystals have to be resilient
Yes.
to stress.
Right.
Okay.
Right.
If I take a diamond and I press it or I heat it up, the diamond is going to retain its temperature.
Right.
So how did they actually test that here? Well, what you can do is you can poke it,
Yeah.
and the pattern stays, which means that it is a true time crystal.
Right. It is resilient to the
poking.
The poking of it already has.
Yeah, it's got some time crystal going through, and then when I poke it, the time crystal sort of it recovers. Where I poke it, of course, it's gonna mess up, but I remove it, and then the crystal regains its properties.
Yes.
The other thing they did was they would vary the brightness of the light.
Yes.
Because it can't be that it depends really heavily on the brightness of the light. So they randomly varied the brightness of the light. The crystal kept going, which means that what this is really an intrinsic property of the material itself rather than the drive that's coming from the outside.
Yes, yes,
right.
Yeah, no, that's exactly.
Yeah,
okay.
And then the final nail in the coffin for me was what they did was they would turn off the light, and then they would turn it back on again. And if this is not a true crystal, if this is simply a response to the light, then when I turned it back on, the crystal would start up at exactly the same phase every time. Mm-hmm. Meaning I turn it on, 5 minutes later, the same pattern. 5 seconds later, the same pattern emergence at exactly the same spot. Mm-hmm. But what would happen was they would turn it off, and then they turn the light back on, and it would randomly order itself. Mm-hmm. The same crystal would start, but at different starting points in that wave. Mm-hmm. Do you see what I'm saying?
Yes.
Like the phase offset was completely random.
Yes.
Which again tells you this is not a property of the outside drive.
Right.
It's a property of the material itself. So this is truly a time crystal that is macroscopic, and it's something we can see.
This is so
right?
This is really fascinating.
It's really cool. And like, okay, you might be thinking, okay, this is cool, right? Then I got into reading about the applications.
Okay.
Okay.
Yes. Yeah.
The applications for this are like science fiction to me. Okay. Most of them have to do with like cryptography and security. Okay. First one I'll tell you about. Imagine we make this thing cheap. We can stick it on a dollar bill.
Oh, right. As a cryptographic signature.
As a cryptographic signature. Now, if you want to test whether your Benjamin is a real Benjamin, you take your iPhone flashlight, stick it on there. It's going to have this pattern, mm-hmm, right? Mm-hmm. Because all it needs is an external drive. Mm-hmm. And the pattern is, we can make it really hard to duplicate.
Yes.
Right?
Yes.
So you know that strip that's on the Benjamin?
Yes.
We can have that strip be a time crystal that like literally propagates.
Yes.
Right?
Yes.
And then you'll know, okay, that's a real one.
It has a signature that only.
And it's going to be so hard to duplicate.
Right.
Right.
That's
so cool.
No, that's very. That's actually really.
Yeah, and the other one is like 2D. Like, so usually we have 2D barcodes. Like a QR code is a 2D. Now you can have a 2D plus one barcode. You can have a QR code that is 2D, and then when you shine a light on it, the QR code itself changes into different QR codes. You can have multiple QR codes on top that have different periodicities. So that, like, let's say one is like 2 seconds and the other one is 3 seconds and the other one is 5 seconds.
Yes.
Well, then the next time that it's going to become a full QR code is going to be 5 times 3 times 2, which is 30, right?
Yes, yes.
So you're going to have to wait 30 seconds to get the actual QR code, right? You can imagine you've introduced a whole new dimension.
Yes.
To security,
a manipulatable dimension.
Yeah, and the whole point is this is at room temperature,
right?
And it's macroscopic. It's something I can see. I don't need a telescope or like weird ions and lasers to actually. Oh, look, it's doing the thing.
This is why I made the LK99 reference, not because of whether it was real or not real, but because it's room temperature and macroscopic.
Yeah,
and the reason why that's material is that means the transition from theoretical to production application.
Yeah. Now we just got to make it cheap, which is honestly kind of like the easier part of the innovation.
Yes,
right?
Yes, exactly.
You know,
it's an engineering problem.
Yeah. Now it's like, okay, because we can make LCDs real cheap now.
Right. This is,
and like this, it's not. It doesn't need a power source. You just need to put it on there. The power source is the light that I'm going to shine on it. It's kind of cool.
I'm seeing from the abstract here. Their potential technological utility includes optical devices, photonic space-time crystal generators, telecommunications, anti-counterfeiting design.
Yeah.
And again, this is just a first. We haven't even.
Yeah, I mean, I only talked about the anti-counterfeiting and the security part, but yeah, as you said, devices, all sorts of stuff.
There's all sorts of implications in terms of what we can get out of now this fundamental.
Yeah.
Like implementation experimentally at room temperature in a macroscopic form, which is
Yeah, I mean, there's a reason why it was like picked up by so many news outlets. Right?
Yeah, it was covered by a lot.
This is quite a big deal. Yeah,
this is quite good. They didn't get they got Nature Materials. They could have put it in Nature, but they said,
yeah,
we'll put it in Nature Materials.
They probably tried in Nature first. Usually everyone does.
First time crystals that you can see. Really interesting story, and the background is also
a great one.
Helpful to understand. We live in LA, so we know a lot of people that like to talk about crystals. This is a little bit different than those crystals.
Yeah, this one actually works.